Welcome everyone, this is page 5 of the fall semester 2014 final exam for Math 234. In this problem we're given a vector field, and our first task is to show that the curl of that vector field is equal to the vector 0. So I'm going to calculate out the curl. Remember, the curl is equal to this del cross f, right? And so usually I kind of just write down i's, j's, k's, the partial with respect to x, the partial with respect to y, the partial with respect to z, and now I do my p, q, and r. So in this case, my p, my first component here, is 2x plus yz. That's kind of a long one. My second component here is x plus xz, and my third component is xy plus 1. Alright, so that took up a little bit more room than I was expecting, but fine. So now I'm going to take my cross product. So when I take the cross product, I'm going to have stuff with i's minus stuff with j's plus stuff with k's. And if all goes well, right, this is going to be equal to 0, 0, 0. But let's go ahead and verify, right? So this isn't just, write this 0, 0, 0 because we know what the result is, right? We actually need to show our work. So, okay, I'm going to cross off the first column and the first row. So I'm going to have the partial with respect to y of xy plus 1, so that's just going to be x. And then I'm going to subtract away the partial with respect to z of x plus xz, so that's going to be another x. So yes, x minus x, that's going to be equal to 0. So far, so good. All right, how about if I cross off the first row and the second column? So the partial with respect to x of xy plus 1, that's going to be y. Subtract away the partial with respect to z of 2x plus yz. So that's just going to be y, right? Because again, there's no z's in the 2x, there's no z's in the y, so if you take the partial derivative of yz with respect to z, you just get the y. Okay, so again, y minus y, that's going to be negative 0. Well, negative 0 is the same thing as 0. And if I cross off the first row, third column, I'm going to have the partial with respect to x of x plus xz, so that's going to be 1 plus z. And then I subtract away the partial with respect to y of 2x plus yz, so the derivative with respect to y of y is going to be 1, and the derivative of yz is going to be z. And so I have 1 plus z minus 1 plus z. So again, this right here was telling us that our answer is 0. Right? So the vector is 0, so it's 0, 0, 0. So if you don't get this result, this is an indication that we've made a mistake and we should go back and double check. But we certainly need to show this work, right? Because it's not just about the answer, it's about how to get to the answer. So you definitely need to show this step, right? The x minus x, y minus y, 1 plus z minus 1 plus z. That's an important step in order to get full points. All right, that is part A. We've shown that the curl of f is equal to 0. Next up, find a potential function. That is a little f, so that way its gradient is equal to the vector field. So remember, we actually had this nice theorem that says if we have the curl is equal to 0, then the vector field is conservative and you can find a potential function. So that's what this is saying. Okay, now that we know we have a conservative vector field, let's go out and find a potential function. So we have a technique for this, right? If this truly is a potential function, right, then this should be the partial of some f with respect to x. This should be the partial of some f with respect to y, and this should be the partial of f with respect to z. That's what it would take in order for this to be truly, a conservative vector field, right? That it comes from the gradient of some potential function. And so gradients, right? So f sub x, f sub y, f sub z. Okay. So let's go ahead and calculate out then what would f be. So I'm going to start with by integrating f sub x with respect to x. This would be maybe a good starting point for what should my potential function be. So in this case, we know that f sub x should be this first component. So that's going to be 2x plus y plus yz. Again, I'm integrating that with respect to x. And so when I do that, I get x squared plus xy plus xyz, and the only problem here is that, right, when you take a derivative with respect to x, you lose all of your information about y's and z's, right? You can have a crazy function here, and so long as it only has y's and z's in it, when you take the derivative of it with respect to x, all of it goes away. And so that's why we have a function left over here that's that can depend on y's and z's. So now our goal is to try to figure out what is this function. So let's go ahead and maybe let's take the derivative of this with respect to y. So if I was to take the derivative of this with respect to y, I would get x xz plus the partial of g with respect to y. Again, I don't know what this is, so I can't really write down any more. So I'm just going to write down the partial of g with respect to y. All right, and if this is true, right, then this should be equal to f sub y. So f sub y in this case is x plus xz. So x plus xz. So you can see actually there's some cancellation here. And we're left with 0 is equal to the partial derivative of g with respect to y. And so if the partial derivative with respect to y is 0, that means there can't be any y's, right? That all the y's are gone. So actually this is a function in terms of just z's, right? So I can go ahead and write that this function actually only has z's in it. Otherwise, the partial derivative with respect to y wouldn't give 0. Okay, finally, let's go ahead and take this and take the derivative with respect to z. So if I take the derivative of this with respect to z, well, let's see, I'm going to get 0, 0, xy, plus the partial of, well, actually we found that this only has z's in it, so if you'd like to, you can go ahead and rewrite this, just g of z. And I need to take the partial derivative of it with respect to z. I'm just going to use the prime notation. I'm going to do g prime of z, right? It only has one variable, so this is not ambiguous or anything like this. And so we need to set this equal to, right, f sub z. So f sub z is xy plus 1. So xy plus 1. And so again, we can see there's some good cancellation. But it doesn't all cancel, right? So this says g prime of z is equal to 1. So if you were to integrate both sides, right, we would get that g of z is equal to, and again, we're integrating with respect to z, so this is going to be z plus some true constant of integration. So we found that g of z is equal to z plus c. And therefore our final answer is going to be, well, we're going to look at this right here, but then I'm going to substitute in g of z. So I'm going to do x squared plus xy plus xyz plus, everywhere I see that g of z, I'm going to put z plus a constant of integration. Now actually we don't need that plus c in this case because it says find a potential function, right? If it says find the potential function, or better yet, find the most general potential function, right, then you would want this plus c. But when it just says find a potential function, really you can do plus 0, plus 100, plus whatever. So I'm just going to leave this off in this case. All right, so this is a potential function. All right, finally, part C, evaluate out a line integral where C is a curve from the point 0, 0, 0 to the point 2, 1, 1. So this is important, right? When you have a conservative vector field, if you go out and find a potential function, there is this great theorem called the fundamental theorem of line integrals, which says this line integral right here can actually be evaluated by doing f of b minus f of a, where f right here is the potential function, b is your ending point, and a is your starting point. So right, this is saying that we have f of 2, 1, 1, subtract away f of 0, 0, 0. So that's my ending point minus my starting point. So I found my potential function up here. Let's go ahead and plug in these values. So everywhere I see an x, I'm going to plug in 2. So let's see, that's going to be 4 plus, okay, x times y, that's going to be 2 times 1. That's going to be 2. Plus x times y times z, so that's going to be 2 times 1 times 1. Plus z. Minus f of 0. So f of 0 is going to be, well, zeros all around. So subtract away 0. So in this case, we're going to have, let's see, 4 plus 4 is plus 1, so that's going to be 9 minus 0, so altogether 9. The claim is, wasn't that so much easier evaluating out that line integral using the fundamental theorem of line integrals rather than actually evaluating out, right? We'd have to parameterize a curve and all that sort of stuff. This was much, much easier. All right, that's it for page 5. Thanks for watching, guys. I'll see you next time.